this class, we should be able to finish most of the material here regarding data visualization, which introduces a topic that's very obvious and is straightforward. So if you sit back here and you look and think why I'm looking at these graphs, you understand that these principles have been used graphs for many years. But the purpose here is really to emphasize a few key rules that you can learn to make your graph stand out and make the user consume that graph faster. So we use the terminology decoding the graph. So you look at the graph and you decode it. The person who's created the graph has spent time taking those data numerically and coding it into a graphical form. You as the consumer are decoding it back and extracting useful information from the data. With data, we don't have information. To get information from data, we have to decode or translate that graph and extract the value from it. So assisting your user to do that decoding very rapidly and get the right message rather than an incorrect or distorted message is critical. So it's very often that newspapers, for example, are the most common source of this, will bias and distort the data in the graph so that they can convey a message that they want. They'll put a spin on it. So politicians, newspapers will do that. The general rule that you should obey, this is one of the key rules for good graphic design, is to take your data and maximize the ink that you spend on emphasizing the data. So if we take into account this ratio, the ink I use in surface area for the data divided by the total ink used in the entire graph. So not counting the white space, but if I take the total number of pixels in the graph, not related to the background, and that's my denominator, and then the total ink that actually represents the number itself. And I call that ratio. I should try to maximize that. In other words, can I take an eraser and eliminate material from that graph and still essentially convey the same information? If you can erase information, you don't have an efficient graph. Erase and erase until you get to a point where you cannot erase anymore, and that's a good minimal graph that obeys this principle of maximizing the data. So we ended off the last class with bar plots as saying, in many cases, they're not an efficient form of graphic because the left edge of the graph, this left edge black line, this right edge black line, this top horizontal line, all convey essentially the same information, that this bar is 132 high on the y-axis. The surface area covered by that ink is a great waste of ink, conveying essentially the same piece of information. That number itself printed up there conveys the same piece of information. Far more efficient in these sorts of plots to show them as time series, where we're essentially just connecting these points and showing those data discretely. Much, much less ink being used. That graph on the right has got to maximize the data ink compared to the graph on the left. And then I ended off with this plot, which really is so wrong on so many levels. The use of color is awful. The principle of the data ink carries through there. There's awful legend here. The fact that the y-axis is non-existent. The x-axis is called total, when really the x-axis isn't a total at all. The x-axis is representing time. The ability to decode this information takes me a long time to figure out what's going on here. To cross-reference orange with this color back here, it's really an awful plot. So bar plots then, just to summarize where we ended off last class, use horizontal bars by all means. Don't feel that your horizontal, that your bar plot must be vertical. Reorder the categories. So bar plots always have a categorical axis. Reorder that categorical axis to tell your story. So if you're trying to tell a story here on which are the most important expenses or the largest expenses, reorder that. No need to use the default alphabetical ordering or the default ordering that the software would provide for you. So that helps decode the data in a fast way and it helps emphasize what you want the reader to learn. Interestingly is you can often place your labels inside the bars, so that can minimize the space taken by the graph. Let's move on to box plots. box plots are a very efficient way of summarizing a single variable. So a univariate variable, we can summarize it down in 5 numbers. We will go through some of these concepts of percentiles and quartiles and medians in the next class. But essentially what the box plot does is it gives you the minimum sample value and the maximum sample value in some box plot software. These 2, 3, and 4 elements, they're usually consistent amongst different software packages. Whereas the first and the last one here, some software packages will either display the minimum or the maximum. Others will display these whiskers at the median minus 1.5 IQR and the median plus 1.5 IQR. What is the interquartile range? To understand that, we need to understand what the quartiles are. So every data set, a univariate column on the data table, we can sort those data from low to high, and the point at which 25% of our data lie is called the first quartile. So if I take my data from single column, sort it from high to low or low to high, doesn't matter which. So here are my numbers numerically. Here's my lowest, here's my highest. The midpoint over there, my second quartile, you know that one very well as the median. But then the point which separates 25% from 75%, that's called the first quartile. The point that separates the 75th percentile is the third quartile. So what a box plot will do is will show you those quartile values as well as the median, and then this distance from the first quartile to the third quartile is called the interquartile range, or IQR. It's a very efficient measure of spread. So a data set with a large IQR has a large spread. It's a very robust measure of spread. So we'll talk about robustness in the next class. But outliers in the data set, my IQR is not going to be influenced by outliers. So here's a nice illustration from Wikipedia. So I put this comment. If there's ever a statistical concept that I don't explain well, look it up on Wikipedia. There's people that explain things very, very clearly and have great illustrations. I thought this was a nice illustration showing the box plot as it applies to a perfectly normal distribution. Now, the data that we will deal with are never normally distributed perfectly. But if we had to have a data set that were closer to normal distribution, here's our median, corresponds exactly to the peak on the normal distribution. The first quartile is the point which separates 25% of the data from 75% of the data. So that this region between the first and the third quartile captures 50% of our data points. So this 24.65 is because they haven't accounted for that last tail. If you go from that point all the way to the end, that's 25% of the area, 50, 25. So the interquartile range spans the central spread of the data set. 1.5 times the IQR from that point down is where the whisker is located. So it's a measure of the extreme of our data set, and so is the upper point over there. So some data software packages will show the actual extreme value, the actual minimum and the actual maximum. Some software packages will show this with the median plus and minus 1.5 times that. So it gets a very good initial summary of the univariate variable. I'd like to show you this interesting example where this was used in a company I worked with. Right as soon as I graduated from Mac, I worked for a few years for the NACC, and the first project I had to go on was this trip to Quebec. And I was surprised. I was surprised by how much technology there is in a sawmill and the level of sophistication just to get a 2x4 at the end of it. So here's a scan of a log. So these companies take these logs through a laser scanner, and as the log is traveling through and about to be cut, it gets the scan just as it enters the saws, and an optimizer calculates the optimal way to rotate that log through the saws to get the most dollar value for it. So how many 2x4s, how many 2x6s, and what orientation. And it will spin that log around, up and down, left and right, and forward and back, and even twist it through the saws to get, because some trees that grow on slopes will have a bend to them, so to counteract for that, it will actually twist the tree through the saws to get the straight cut at the end. So what I thought to show is just some of that for you, to give you an idea of how these mills work and what it's doing. And this is a long video, so just the noise. Debarked at this point, so simply take the outer edge of the bark off, and so there's no optimization up to this point. But then around here, we can see these debarked logs going in, and I'll point out where the laser cut up, we see that we get several boards coming out here, and these are the boards that we're dealing with now in this case. So what we're dealing with here, and this company was interested in, was the thickness of these boards. So they measure them through another set of lasers. Every board, after it's been cut, goes through another set of lasers, and it measures the thickness at 6 locations on that board. The board's target thickness should be 1680 mils, and the actual thickness that you get it when you buy it in Home Depot or Rona or so on is 1,500. So that board will shrink over time as it dries from the way from the sawmill to where you finally purchase it. So a 2x4 or 2x6 really isn't 2 inches thick, it's 1.5 inches thick. But when they cut it in the mill, they aim for 1680. So what the company does is they monitor that thickness. Here's showing for the past 100 boards that have come through. They can look then and efficiently see on a single plot how well they're doing from 1680. Interquartile range tells them the variability around that target, and then these extreme outliers can point out problems with the saws. So the fact that this board's always at point position 1 has these extreme outliers can indicate that the saw at that position is starting to go dull or has some offset that needs to be corrected. And here's an interesting one. Here's this interquartile range, not balanced. The fact that the median is far away from the upper quartile and closer to the third quartile, that indicates an issue with the relative variability. So box plots get you a very quick summary of the distribution of the data as well as the extremes. And they're great for comparison. So here we're comparing 6 box plots from left to right. Great way to compare data, especially, they have to be, the criteria is to make that comparison accurate is that those have to be the same type of variables. So thickness, thickness, thickness at 6 different locations. So you'll see some variations on this. There's no unified agreement on how a box plot should be shown. Some people will use a mean instead of a median. Some people will show outliers. Some people will use the IQR instead. Some people might use the 2nd and 98th percentile rather than those 1.5 IQR. So just check the software package that you use. Check the help function for it to make sure that you know what's being plotted. An interesting variation on that is to superimpose a density histogram on top of the box plot, and then you get what's called a violin plot. So for that same data set, then But the same information that the box plot contains, here's your median, IQRs, and then the extremes. And these circles represent discrete outliers. There's your whiskers over here that represents the bounds. But then you've got superimposed on that the density histogram. Here we can clearly see position 3, a large tail out here. Okay? Position 1 as well. I'm sorry, position 6 up here. A much longer tail than we would like. Ideally, we would want all our boards to be very close to target with a small distribution. So we're getting that distributional information explicitly in the biological plot. So all these plots in the notes here were drawn with R, and I will be putting up a tutorial on the course website showing you how the commands to generate these plots. And you'll be required to do this for the assignment as well, which I'll post later today or tomorrow. Okay, so the next plot I'd like to look at is a scatter plot. Now, scatter plots, we've been looking at plots that show a single variable, so thickness or a single number at a time. Scatter plots start to go to 2 variables. And the implicit assumption of a scatter plot, or the implicit intention is we're asking the viewer to draw a causal relationship between those 2 variables. Whether a causal relationship actually exists or not is one thing, and I'll talk about some examples of that now. But that's what the intention is of showing a scatter plot, whenever you want to indicate some form of relationship between 2 variables. So here's one that we're comfortable with, the vapor pressure related to temperature measured in Fahrenheit. So this is data from a distillation column in Petro-Canada over a period of a few months. It's not a perfect correlation that we learn about. In your Antoine equation, you might think you get this beautiful straight line that relates the vapor pressure to temperature. Real data, there's measurement error, there's all sorts of issues. Lab error in measuring the vapor pressure, calibration error on temperature. But the general trend is exactly what we expect. In this case, there definitely is causality there. We know that from chemistry and engineering perspective. But here's, and you'll see countless examples of these. If you look for them in any newspaper publication, you'll always see dubious correlations and causality assumptions being made. Here's one where we're showing the bone mineral density of a patient. So essentially bone mineral density is a measure of osteoporosis. And on the x-axis, we're showing the number of white hairs per square inch on the skull. So clearly a negative correlation between these 2 variables. People with lots of white hair, low bone mineral density, high tendency for osteoporosis. Cause and effect? Yes? Aging? So if I was old and I dyed my hair brown, would I go back to a high bone mineral density? No. So cause and effect is very clear. When you change one variable, the other must change. Okay? The moment you can change one variable without the other variable changing, you do not have cause and effect. This is what the design of the experiment section of the course is about. We'll get to that in a few weeks' time. DOEs break causality, break any correlation trends, and expose causality. The only way you can ever show causality is by doing an experiment. If you have not done an experiment, you cannot state that there's a cause and effect relationship. You can infer that there might be one, but if you can't do an experiment to prove it, you cannot say that there is. And I'll show another example of that in a few seconds here. So, scatter plots, some things that you can do to make the scatter plots really good is to tighten up every axis so that you're only focusing on the data. The default settings in Excel and MATLAB often are to leave a lot of space on the axes that really have no data beyond them. So the typical problem with Excel might be that they'll take this axis up to 2000 by default and down to 0. Okay, so MATLAB will do that as well. R has been actually is an excellent package for data graphics, and that's only because the people who have been involved in the development of the R language are data visualization experts, like William Cleveland. And so they've emphasized and brought in the default settings in the software package so that you get good graphs almost with no extra work. If you were doing this in Excel, you would have to tighten up the X and Y axis down in order to get a good scatter plot. Avoid heavy grid lines. Notice here in R, no grid lines by default. If you want to add grid lines, you have to manually add that in. And that's because the human eye, in many cases, doesn't need grid lines. We can are excellent at drawing vertical and horizontal lines without them actually being present. There's very minimal use of data ink, and don't distort the axis. So some people will show, especially if you've got the same two variables, so length and length, say on the one axis or the other, you stretch one of the horizontal axes to make it fit in the page. In landscape mode, for example, you're distorting the picture, you're distorting the extent of the correlation that may or may not be there. The other thing is, we are comfortable with scatter plots in engineering and science. But there's this unfounded fear that people in the general public are idiots and will not be able to understand the scatter plots. And that's not something I'm saying lightly. There's a lot of evidence. So here's William Tufte's book on the visual display of quantitative information. And he's gone and looked at media going back to the early 1900s and shown that in any of the publications in the United States, like the Time magazine, the Wall Street Journal, in Great Britain, the Times, 0.0000% of scatter plots. You'll never see plots with two variables. But if you look at Japan, there's several publications right at the top of the list, German, European publications. They commonly have scatter plots in their publications. They recognize that people can infer what's going on in them. It's not that you need a university education to understand what a scatter plot is about. This is important. When you're working in a control room, we'll often see that in a control room, there's no scatter plots. There's only univariate time series plots, or bar plots. But there's no reason why the operators cannot see and understand a two-dimensional data plot. They're as qualified as anyone else to understand and interpret that with a minimal amount of training if required. So don't feel that you need to dumb down your data to univariate axes in order for people to decode and consume what your information is. Here's an interesting example I wanted to talk about. I saw just the other day. This work was done some time back, but only been published recently. It shows the relationship between tetrahedral lead that used to be in leaded gasoline probably before the time that you owned cars yourselves. You probably weren't aware that most gas pumps were leaded gasoline. And has been phased out now for many years. There's been this correlation that's been noticed with a lag of 23 years between leaded gasoline's presence in the air, so atmospheric lead, versus violent crimes. So this author has plotted the data, violent crimes in brown, lead in the air in blue, and shown a very strong time series correlation between the data. Notice though that there's an offset between the different plots. So in blue is the level of lead, and then 23 years later in brown is the level of crime. Cause or an effect, or pure correlation. Cause and effect. Any ideas why? There may be a relationship with pregnancy, and it enters your bloodstream and changes some chemistry in your brain. Can we do something to determine the cause and effect?
Not ethical.
Not ethical. Okay, absolutely. And this is the problem that all the social science studies have, is ethically, we cannot go and find a community and pump lead into the air and see if 23 years later crime increases. We would not ever be able to do that. As engineers, we have it so easy. We have it so easy, and we must take advantage of it. We must take advantage of doing our experiments because we can. We can easily prove and disprove correlation and cause and effect. These studies, there's multiple of these, but I'll have a few in the assignments and so on, that show dubious relationships. Now, this particular relationship was interesting because not only did the author do this for one situation, they went and did it in multiple states. So multiple states phased out gasoline at different times. And that correlation of 23 years holds in different jurisdictions. They did the study in Canada, they did it in Australia, they did it in multiple European countries, and every time that same correlation has shown up. Can we still say that there's cause and effect? We're now getting to the point where it might be there, but it may not be there, right? We can never say conclusively that one variable causes the other in this particular case. Though it's an excellent way of trying to get to a closer interpretation of cause and effect is by looking at it in multiple jurisdictions. So in different states, different provinces, different cities, and phased it out. Differences between the rural areas and city areas where there's a higher density of cars versus rural areas where they're not show weaker and stronger correlations. Okay, so one thing that could be interesting is to take these data, here they're shown as a time series, to emphasize that time-based effect. But I could just as well take the data points here in blue and orange, blue and brown, and take each one of them and plot them on an X and Y axis and show a scatter plot of the data. Okay, so for this particular data set, I can convert the time series plot over to a scatter plot of discrete points, and I should end up with something that shows a positive or negative trend. So if I'm plotting lead on one axis versus crime on the other axis, what sort of trend would I see? Positive trend. And you should see something along these lines. Okay, so I can always convert a time series with two variables on them to a single scatter plot with my two individual axes. And I can draw lines across like that to emphasize the strength of the correlation. If I was doing this for multiple cities, multiple countries, multiple regions, I could repeat these scatter plots over and over to show that level of strength. Or I could even more simply calculate that correlation coefficient slope and simply report that in a data table. So you can always take your data, go to graphical form to understand it, and then come back down and summarize this complicated, or not complicated, but these many set of numbers down to a single variable, an R squared, or a level or slope coefficient, and then translate that into a data table now where I report R squared or slope for city 1, 2, 3, 4, and so on. Okay, so go from raw data to plot back to raw data is very common in statistical practice. Other embellishments you can add to get some sort of sense of spread is to add histograms on the side. They may help in certain situations where you want to see that spread and the density for each axis. And then here's the interesting thing I'd like to talk about for a few minutes and show you a video. Scatter plots are two-dimensional, but we're not constrained just to two vectors of information. We can add a third variable to that two-dimensional world by using different marker sizes. So here, the size of the circle that's used on my x-axis, I've got income per person. On my y-axis, I've got children per woman. So countries down here, low number of children born per woman, high up here, higher levels of fertility. So the fertility axis on the y, income per person on the x. Cause and effect. Higher income, higher GDP per capita, lower number of children. Countries that are poorer, lower GDP per capita, greater levels of fertility. Again, can we ethically do an experiment? Put people in poverty and see if they go to have more children? Likely not. However, there's strong evidence that this relationship holds across many jurisdictions and many regions. We can add more information to that two-dimensional world by using a larger and smaller marker. The large markers represent the population size for that country. So here my axis is income per capita. I've taken away the number of people as a variable. I've divided through by the population size. So I've lost population size of the variable. Bring that back in again, though, by using a marker size that's proportional to the population. Use a color scheme that shows life expectancy. Here, blue colors represent 20, 30 years of life expectancy. Red colors represent longer life expectancies. So instantly I can see countries down here have longer life expectancies. These countries have lower life expectancies. 4 variables on a 2-dimensional plot. I can add a 5th variable. If I created a video of this over time and I show these markers moving, I'm showing a 5th dimension of time. I can add a 6th variable with the technology we have now of 3D glasses and 3D projection. I can add a 3rd vector into the plane and see those circles moving in time and changing color. 6 variables in a 2-dimensional world, essentially. There's no reason why we can't have that in control rooms and in operator screens to get a very good depth of information and extract information. So what I'd like to do is to emphasize the point is I can't explain it nearly as well and with, I don't know what the word would be, but you can make up your mind once you see this video.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew. So, here we go. First, an axis for health. Life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only the UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now, we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the difference between the countries of the world was wider than ever. The United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up to the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle. But there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
So that software that he used was, the company was called Gapminder. It got sold to Google. Google has now incorporated that technology into a number of their free visualization tools. So online in Google, you can create those same plots. And that particular visualization that he has is easily available, as well as they've got data from all these countries, but not just fertility and GDP, but lots of variables that are available from the censuses from the different countries are available to plot. So you can spend hours on that website looking at interesting correlations between the different countries and interesting visualizations of it. Let's move on then and just quickly talk about tables as another form of effective visualization. One thing to recognize about tables is that they're good for comparative analysis. Like the box plot where we showed 6 boxes next to each other and we were able to compare different variables of the same type, tables allow a bit more flexibility because the categorical axis is either your rows and or your columns. So depending on what you have, you can be comparing from column to column to column, or you can be comparing from row to row to row. Either one is an option, or both at the same time. In this particular data table, I've got 5 different cars. These are my categorical objects. And then I'm comparing various pieces of information for each of the car. What's my monthly insurance payment for that car, what it might be, how much interest I would pay if I had to take out a 48-month loan, what my down payment requirement would be, etc. So I'm comparing then between the rows as I'm going down. I can, obviously, as we've seen before, reorder those rows to make the table tell a story that I'd like the reader to see more clearly. If I had a list of 30 different cars here, it would be much harder to work and find through those 30 rows which car has the smallest monthly insurance premium. It's doable by scanning up and down a few times, but make it easy for the reader. Reorder these 30 rows from lowest to highest monthly insurance payment, and you're immediately telling the reader this is what you want them to get from the table. Tables have a reputation of being hard to use, or you may have been told to always plot the data in the table. Don't show me the raw data. Shove it into appendix, I don't want to see it. That's typical of our lab reports. It's really unnecessary. Tables are actually extremely effective at getting information out for moderate-sized data sets. Moderate-sized data sets, you do not need to go over to a graph to get the relevant information from the data. You can, with proper ordering of the rows in the table, or proper ordering of the columns, really tell an effective story even with the table. Here's one example for aluminum company was measured defects on different categories of products. So in my rows, I've got product A4636, A2524, etc. And for that product type, I've measured 5 different defects A, B, C, D, and E. So as the product comes off at the end, one day they might be making this product, and the next day they'll move to another product. And then over the year, they produced several runs of all these products. So this is the annual summary for for the products, and they've counted up the number of defects of A, B, C, D, E, and so on. And they can now use this data table quite efficiently to target which defects cause the most problems. So defect E, by number, clearly causes the most problems over all products. But other defects types might cause more problems for a specific product alone. Those sorts of questions can easily be gathered and answered from the data table. So for example, I can see that defect A really doesn't ever impact A4452. And if defect A and A4452 was really one of the defects, and was a highly valuable product, I don't really need to worry too much about what defect A's impact is on this. So these questions and answers that the reader might want to come up with in their mind can be done if you give them the data table well formatted. So my key point here is don't feel that data tables should never be shown to the reader. They really are an effective way of getting at numbers. Here's some questions I posed that you can work through and look at that data table. I'll leave that to you in your own time. The main point here is when we're going through a data table, we're scanning across the columns or we're scanning up and down the rows, and we're comparing the different categories to each other. So in this table, I have 5 categories of defects, but I also have multiple categories of products. So a categorical variable here and a categorical variable there. One other issue related to data visualization is we'll often summarize tables with pie charts. So here's my own version of it. I made these pie charts before I knew better. When I was working at the MACC, I was asked to summarize where MACC graduate students ended up finding employment, in which sector and in which countries. So I looked at the data and I summarized it by a pie chart. And a few months after that, I came across this article about why pie charts really are not an effective form of data visualization. There's so many different reasons for it, but one of the main reasons is that the human eye is very poor at judging angular information. We find it hard to judge angles and the surface area related to a particular angle. We're very good at judging straight up and down lines and horizontal lines. If you look at a painting on a wall or a picture on the website, you can see if it's tilted by even 0.1 or 0.2 of a degree. We've got very good resolution close to the horizontal and close to the vertical axis. We do not have that on diagonal lines. So this article here, you can click on that link in the electronic version of the notes, is a very readable 4 or 5 page PDF that shows some excellent examples on the poor use of pie charts. Here's some others that you may recognize. These 3 over here are from the SDL reports from fall end this year or last term. So different groups had used pie charts to try and convey information about their project. Really, really hard to consume this information. It's the breakdown of the economic cost of various units in their flow sheet. So clearly it's clear that this unit is the largest capital cost item, but from this pie chart alone, it's hard to tell what the breakdown is through to the other units. You're really not conveying any useful information with that pie chart. This one is obviously a waste of ink. 88 and 12% can clearly be just written in text. There's no need for a pie chart for that. Again, here this distorted 2D view breaks the visual understanding of where the breakdown comes from. And then here, these shadings and colors and gloss effects really are not conveying the information. And then to make it worse, they've added the information on as text anyway. Why not just show it as a table? So whenever you have this temptation to make a pie chart, stop and just put it as a data table. You really are not benefiting anyone by using a pie chart. And it's not just that we want to tell you not to do this. There's a number of studies that have shown that there is no benefit at all to pie charts. So please read that article. It's a very short one, but it explains very succinctly and shows many examples of why pie charts are not an effective visualization. The reason for its wide use is, again, this unfounded fear that the people in the public that consume these data are idiots. So newspapers like Hamilton Spectator, Toronto Star, Global Mail, they're filled with pie charts. Filled with them because they've got this implicit assumption that their readers cannot actually understand any data in the table. Another issue related to tables is, as I said there, the ordering of rows. We've discussed that before. And then one other final point is on the use of grid lines. This table here on the left-hand side has much fewer grid lines. So I've taken away a lot of the ink of the graph, and I'm still conveying the same amount of information. Our human eye is very good at picking out this implicit white space forms the column boundaries for us without the need to actually have a vertical black line there that breaks it up. This dark edge on the perimeter of the table is necessary as well. So to minimize the use of data ink applies to every detail, the graph, the grid lines in the time series plot, in the scatter plot. We can often get away with deleting those out. One other thing related to data tables, and you'll see this in the design experiment section, is when we're comparing two variables. So comparing two treatments, I'm applying treatment A and treatment B, and B is a coating that I'm applying to a surface. And I'm comparing what the corrosion resistance is for treatment A versus treatment B. That's my categorical variable in the columns here. My categorical variable in the row is different products, so K135, K136, P271, etc. So I've got my K series, my P series, and my S series of products that I'm applying treatment A and treatment B. I've got another set of experiments where I've not measured only corrosion resistance, but I've also measured surface roughness. So the same idea of surface roughness under treatment A versus surface roughness under treatment B. Here, a data table can help answer some of our questions. Which one of those treatments leads to greater corrosion resistance? Which one leads to a higher or lower surface roughness? I can certainly look through that table, but it is quite hard to find which treatment might be the more effective treatment at reducing surface roughness, for example. Here's an effective way that you can look at the data, and we'll look at this in the DOE part. It takes a while at first, it looks like a bit of a jumble initially, but it is actually quite easy to see what's going on. For this first initial view, we can see that these negative sloping black lines, negative sloping blue lines have reduced the corrosion resistance, going from coating A to coating B. So for the S series and for the K series of products, coating A versus B have reduced corrosion resistance. For the P series, it's marginally increased. So very quickly, I can see the effect of the treatment 1A versus B. Same idea for the surface roughness, but the fact that these lines are all jumbled, and the fact that this red line crosses with that red line tells me that treatment for surface roughness really didn't have any appreciable effect, either up or down. It seems to be random for at least the P series. The blue lines jumbled are crossed over. Again, no effect on the K series, and it seems only to work well for the S series of products. So you can, with some additional plotting here, it takes some time to generate these plots compared to the data tables, but these data tables are not easy to make those judgments. With the graphical presentation, I'm asking the reader, I'm giving the reader some assistance to decode that data and get to some useful information. They can now come to an accurate conclusion regarding treatments of A versus B. Data frames I'll talk about in the next class a bit. What I'll just end off here with is a discussion quickly on color. We're obviously aware that some fraction of the population is colorblind. But not just that, one thing to recognize is that a lot of documents are still printed out and consumed in printed form, and we cannot assume that they're going to be printed in color. So recognize that there is no standard color progression. We often see blues going to greens to yellows, oranges, and reds, so that's a somewhat standard color progression, but not everyone can appreciate that. There's only one color progression that is universal and always works, satisfies the colorblind readers and looks good in printed form, and that's the progression going from black to white through the various shades of gray. And the U9 is excellent at picking up very, very discrete shades of gray. So use that when you want to. Okay, so just to end off with it, there's a bit of general advice to summarize the last few slides here. I'll leave you with that example to take a look at, and you can look at the very gratuitous use of illustration. The key quote here is, if you're prettying up your graph by adding all this junk to it, you're trying to make the plot exciting for your reader. As one of the statisticians has said, if the statistics are boring, you've got the wrong numbers. If you're trying to make it exciting for the reader, you've got the wrong data. It takes a lot of work to get to the right data to get an exciting measure of cost. If you're resorting to these sorts of illustrations, dollar bills, houses, and signs like that, you really are taking the wrong approach. You should be thinking of what you're trying to convey. Okay, so